Okay. So what we're going to be able to answer in this lesson is how big of a difference is big enough for us to say that this actually really is a difference. Does that make sense? Because somebody asked me a question about the homework. Well, in this one example, the difference was like 10%, so I think that's significant. But in this next example, it's only 6%. And like, is that a big enough difference for us to say it's a significant difference? And so far, I've given you 0 2s to tell you like, okay, this is a big enough difference and that is not, okay? So that's a procedure called inferential statistics. And we'll talk a lot about this semester. This is kind of like a baby introduction. So you use the sample evidence to infer something about the whole population. Rather than measuring the whole population. So, think of a good example. So, for example, suppose you want to determine, does drug X, I don't know, let's say, cure muscle cramps, okay, because I'm thinking about my marathon. And you give people drug X and a placebo, and you make them run until they hurt really bad and figure out if they get muscle cramps or not, and you can conclude that, okay, yeah, my drug X is going to help you not get muscle cramps, something like that, okay?
It's an inhumane experiment.
Yes, you do an experiment, and you compare things.
Humane experiment.
Yep, yeah, that one's not very humane, but we'll try to do humane experiments. And hypothesis testing, this is a procedure used in inferential statistics. We're going to go through that for this example, and then we will do a lot more of this later in the semester. So something has statistical significance if a difference like the one observed is unlikely to be due to chance. And this is one slight downside to having not done chapter 1, but I think I made you read some of that stuff. No problem. Yep. Okay. So in the Physicians' Health Study, more than 22,000 male physicians were randomized to either take aspirin or a placebo over a 5-year period. So in some sense, this was an experiment, not an observational study, right? Because you were divided into groups and you were given the drug and you were given a placebo. And they were trying to figure out if taking aspirin reduces the risk of a heart attack. And the rate of heart attacks was 9.42 per 1,000 physicians, or what percent? So what's 9.42 divided by 1,000? 0.942% in the aspirin group, compared to 17.3 per 1,000, which is 1.713% in the placebo group. And they concluded that even though the difference is like a relatively small percentage, like 0.8%, that's not very big, right? It's about, yes, it's about double, right? So, but the thing is that first risk is pretty low as well, isn't it? So this is called statistically significant, and it means that a sample difference this large, a sample difference this large is unlikely to have occurred by chance if there is no difference between the groups. And then you can conclude that the only thing that changed from group 1 to group 2 is that you were taking aspirin, right? And that in that case, taking aspirin probably helps prevent a heart attack. That's the kind of conclusion that you can draw knowing this stuff. We'll talk a teensy bit. Well, I think that's probably a good place to stop because we only have 5 minutes and I probably can't get through very much. So what we're going to do in this section is we're going to figure out sort of the statistical formal procedure for telling if two things actually are sort of like related to each other. Does that idea make sense? So the first thing you have to understand is sort of the statistical vocabulary and how this process works. And there are 5 general steps. The first thing is you make these hypotheses called the null hypothesis and the alternative hypothesis. So the null hypothesis is usually H with a 0. I don't know if your book calls it that, or your book might call it HN and HA, but like the 0 is like null is the German word for 0, I'm pretty sure, so that's kind of where that 0 comes from. So, and the null hypothesis is always that the variables are not related. So null not. The variables are not related in the population. And you are trying to disprove this. I'll talk more about that in just a moment. The alternative hypothesis, that one's also always given as HA, and it's kind of like the opposite of what was said above. So HA is that the variables are related. And this is a bit of a lawyer-like argument. So it's actually why the LSAT, if you study law, is like tons of math logic, because you use that logic in the courtroom to do stuff. So for example, I say, okay, I have this criminal, and I say, well, suppose he wasn't at the crime scene, and I have like DNA that matches his DNA, then it's only so likely that he would be at the crime scene. That makes no total sense. Therefore, he must have been at the crime scene. It's kind of like the logic you use to do stuff like this. You say, okay, well, if they were not related, then the chances are so low that makes like this probably just can't happen. It's almost impossible. Therefore, they must have been related. It's kind of like a contradiction thing. You say, if this thing were true, then it's only this likely, and that's such a low likelihood that it's probably not possible that that thing was true. That's kind of the argument that you make with these things. It's kind of lawyer-like. And the thing you use to determine that, oh my gosh, this is so ridiculously unlikely, is this thing called a chi-square statistic. So it's going to be a little bit magical as to where this thing comes from, okay? Like, I'm not going to lie. But we'll tell you, I'll tell you how to find it. And we'll do it again later in the semester with different context. So Greek letters come up all the time in mathematics. So the chi-square thing looks a bit like a curly X, okay? Chi-squared. And this is used to estimate the association between two categorical variables. And a large, and I'm going to put large in parentheses, there are quotes there because what is large depends on the context. A large value indicates a strong relationship. the stuff we're doing like today and in this chapter is just 2 by 2s, as in there's 2 variables on one end and 2 on the other. We'll do stuff later, I think it's chapter, it's 14 or 15, I can't remember which one, where we have like 2 variables and like 10 variables in one direction. And in that case, what the criteria for what large is changes. That's why I say large in quotes, okay? And once you have your chi-square thing, you find this thing called the p-value. And what that p-value thing is answering what is the see if I can spell this right. I might spell it wrong. Likelihood, or the probability that a chi-square statistic would be this big or larger if there is no relationship. Do you guys know some basics about probability? Like what are probabilities, what numbers must probabilities be between? 0 and 1. So probabilities are between 0 and 1. 0 means not like, yeah. So 1 means 100% certainty, right? 0 means no probability, right? As in like, not at all. So a low probability means unlikely. Does that make sense? And we're going to have a threshold for what is low. Like, the chances are low, near to 0. And large probability means, well, it's probably likely. And so that's what steps 4 and 5 are all about. And to find this p-value, you're going to have to use software. I'll tell you how to use Excel to do it. Okay? I'm sure there also are things you can use, like you can just Google things as well, but I'll tell you how to use Excel. So the steps for determining significance, so steps 4 and 5 are making a reporting decision. When the p-value is less than or equal to 0.05 or 5%. That's kind of like the standard threshold used in lots of statistical studies done in science. You say, okay, if my p-value is less than 0.5, there's less than a 5% chance that this relationship is, like, would actually have occurred in the population. And in that case, when your p is that small, you can reject the null hypothesis. What that means is you can say, okay, it's pretty clear that H naught is not true. Because if that were true, we'd only see data like this like 5% of the time, which is not very often. And then you can say, I'm going to say that the alternative is more likely. And this kind of stuff is used all the time in like biology and medicine, like, and usually it's 0.05. But for other things, it might be a different number. Yeah?
For when we were talking about the chi-square statistic, you said a large value indicates a strong relationship.
They are opposite. So large chi-squared is strong relationship. Low p-value is strong relationship.
Okay.
They do flip-flop.
Okay.
Yep, you're not, yep, that's a good point. They do flip-flop.
So does a low p-value imply?
A large, yes, yes, it does. A low p, but how high is high depends on like how many variables you have, which in this case is going to be constant because we always have 2 by 2. But when we do other things, then it's going to be what is large changes, whereas the p-value that you look at won't change for that stuff. It'll still be 0.05. And the p-value is greater than 0.05 or 5%. We say that the observed relationship, use these words, not statistically significant. We cannot reject the null hypothesis. And one thing that's kind of important is you never say H naught is true. Because there could be lots of reasons that you couldn't reject it. Maybe your sample size was too small, because this depends on sample sizes as well. But this doesn't mean your H naught is true. It's kind of like you don't say a criminal is innocent, you just say not guilty, right? Is that so? And here is, this is specific to things like 2x2s. They're on the question about like how big is that chi-square to be big enough. So you can declare statistical significance when the chi-square statistic is greater than or equal to 3.84. That's what is big, which really, gosh, is like not a very big number in my book. That's what is big in terms of this specific situation, okay?
Is it out of something?
No,
Is there like a max chi-square?
yeah, and it depends on the situation, right? So yeah, okay. So just for now, that's the cutoff threshold, and we cannot declare statistical significance when the chi-square is less than 3.84. It's like on a test when I can't let you use software to get p-values. You may have to make your conclusion using the chi-square statistic. Does that idea make sense? Or I'll give you the p-value and say, oh, what is your conclusion? This is the p-value, and then you can make a conclusion from it. So before we do an actual example, I want you to just tell me, based on these given things, would you reject the null hypothesis or would you fail to reject the null hypothesis? So if your p-value is 0.049, yep, this is less than 0.05, right? So you reject H naught. What if your p-value is 0.755? That's bigger than 0.05. Do not reject H naught. And reverse over. P-values must be small. Chi-squares must be big. Is this chi-square big enough? No. This is less than 3.84, so you do not reject H naught. The reason why those cutoffs are where they are has to do with an area under a curve. Like, it's actually pretty complicated math. Like, you don't really go into it a lot in this class. So and I don't think, in my personal opinion, that's not the best way to treat understanding, but you have to know a lot of math to understand what those, like I'm learning that in the class I'm taking right now. So it's quite complicated. So, but those are the numbers, 0.05 for p-values and 3.8 for chi-square statistic. Okay. So this one's just like another baby step along the way. So you have a survey done in 2010. Students in a statistics class were asked if they favored or opposed banning the use of phones while driving. And one hypothesis was that maybe men and women react differently to this question. And of the 105 female students, 37 opposed the idea and 68 were in favor. And of the 83 male students, 46 opposed the idea and 37 were in favor. So we're trying to determine, is sex related to this opinion on this ban? Does that idea make sense? That's what your null hypothesis should talk about. So null hypothesis means no relationship. So H naught. There is no relationship between gender and what's the other thing we're looking at?
Using phones while driving.
Yeah, so it's opinion, right? It's an opinion about a cell phone ban. And HA is that there is a relationship between gender and opinion. About the cell phone ban. be pretty specific about the situation. Does that make sense? Because if you had said there's a relationship between gender and cell phone usage, that isn't what the question is talking about. Does that make sense? Okay, awesome. All right, so somebody did some magic, which we'll learn that magic in just a second, and they found that the chi-squared was equal to 7.659, and they found that the p-value was 0.006. And both the chi-squared and the p should give you the same conclusion, as in, do you reject h naught or do you not reject h naught? So in this case, is the chi-squared big enough to reject h naught? Is the p-value small enough to reject h naught? Yes. Okay, so in this case, we reject h naught. And I'd like to, at least at this stage, see that sentence. The exclamation mark is optional. So, and in this context, so we conclude that gender and opinion on said cell phone ban are related. Does that make sense? You say, okay, well, gosh, if h naught were true, it's like ridiculously unlikely we'd see numbers that are this different. Therefore, h naught must have been false. That's the logic you're using here. And maybe part C should have come first, but let's actually compute the percentages and see if they seem different. Like, what percent of women oppose this cell phone ban? What percent of men oppose this cell phone ban? So for the females, how many opposed? An out of 105, which somebody figured out was about 35.2%, right? Okay. And so in favor, there were
68,
out of,
64.76.
I wrote 150 when I was supposed to write 105, sorry. So 68 out of 105, which is thank you, 64. Okay. Versus the men, how many opposed? It was 46 out of 83, right? Which is closer to half, isn't it? Yep. And then in favor, there were 37 out of 83, which is approximately equal to 44.6%, right? Okay. Great. So does this seem to support your conclusion that yes, there is a difference? Mm-hmm. Yeah, I would think it does, right? And so the p-value in chi-square is just a way of getting a formal test that also accounts for sample sizes and stuff. Because that makes sense that differences in small groups of people are easier to find than big groups of people, right? Okay. So explain how the difference in these percentages is consistent with what you found in part A. I'll say you can see that females are about 20% more in favor of the ban. This seems like a large difference. Do you guys agree? Suggesting that gender and opinion on this ban are related. Yes.
If those percentages would have somehow been exactly the same all the way, 50-50 all the way across, then it would have been H naught.
That would have, if that were the case, then the p-value that you had gotten would have not been small enough to reject H naught. But how large of a difference is significant depends like a lot on how big your sample size is. Like there was that one we had at the very top of this, like first page of this note sheet about the physicians and the aspirin and the heart attacks, and it was twice as big, but a very small percentage in the first place. So it depends a lot on the context, how big of a percentage difference is big enough to be significant. And it depends on a couple of things, depends on how big the difference is and how big the sample size was. Those two things are what affects it. So that's why you have to have this chi-square statistic thing, because there's no threshold that says, oh, a percentage difference this big is what is big enough to be different. Does that make sense? Okay. So now your question is like, okay, great. How the heck did they get those chi-squared numbers, right? A little bit? You feel that way a little bit? Yeah, okay, me too. Still a little bit magical though. So what you do to find those chi-squared values is you find things called expected values. So these expected values are what you would expect the totals in all the boxes to be if there actually was no difference. And that kind of accounts for the fact that there are, like for this example, like if the men and the women did not have different opinions about cell phone driving, bans and driving, what would you expect the numbers to be in those categories? Because there were different amounts of men and women, right? So how you find this, there's this formula that I'm afraid I cannot explain at all to you why it's true, okay? I'm so sorry. You take the row total times the column total divided by the total M for the entire table, and that gives you your expected value for a row column spot. So like if you have your table, it has 4 spots, right? You do row total for this guy. The row goes the other way, doesn't it? I'm dead, sorry. Row total, column total, big total, and then that goes in that box. That's your expected count for that one box. And you do that for all 4 boxes. One important thing, you should not round to whole numbers. We're gonna keep 2 digits, and I'd like you to all do the same thing so that when I grade your homework, I don't have to check everybody's like different rounding scheme. So 2 digits. And the expected counts in each row and column are going to total to the same as the observed numbers. So for example, in that cell phone one, we had 105 women, right? When you compute these expected values that are going to be decimals, but if you were to add across the ladies' row, you're still going to get 105. Okay, so let's actually, and then once you find those, this is what your thing says. So first for each cell, you find the expected values. And that formula from the previous page was row total times column total divided by the total N. So that's your first step, find the expected values. And then the chi-squared is equal to, remember this big old sum symbol? Which means add them all up, right? So what you do is you do observed minus expected squared divided by expected. So expected are the numbers that you're going to have in your table. Read this thing. Where do you think the observed, or where do those come from? The original numbers, the actual numbers you found, the ones you saw. The original numbers in your table, okay? And because we have 4 places in our tables, there will be how many things we're adding together? 4, 1 for each cell, okay? Not including the total cells, right, as in the ones that count the totals. Okay. So let's do the let's calculate, actually prove that the chi-squared statistic we get is the same as what they told us was in the previous example, okay? So we're gonna make a table of observed counts for sex and whether a participant was opposed or in favor. So I'm just gonna have 1 row for female, 1 row for male. And you can actually do this differently as long as you label correctly, like the sex could go down as opposed to across. And then you have oppose and in favor. Okay. And over here, you're going to be total. How many females opposed the ban?
37.
How many were in favor?
68.
For a total of,
105.
great. How many males opposed the ban? 46. How many were in favor? For a total of,
83.
great. And then 37 plus 46, I think, is 83. Do you guys agree? 68 plus 37 is 105. And the total is 188. Great. A lot of your homework questions will already give you the table like this, okay? But this is just like arranging the words into a table, right? That's not so bad. Okay. So you'll have to help me because that's on your paper. We'll do the next one. The next slide. Find the expected counts. So make the table the same way. So female and male going across, and then oppose and in favor here. And this is where you use the formula for what we had for expected values. The row total times column total divided by the total n. So for this first cell, look at the table above. What is the row total for the female row? 105. What is the column total for the opposed column? 83. Divided by the total n, which is 188. Okay, great. So get me a decimal, and I want 2 decimal places of accuracy. You're gonna look at the third to see how you round. I got 46.36. Tell me if you get that too.
46.5.
What's after the 5?
6.
So that's why you round up. Okay, does that make sense? Yep. Great. Okay, going over. For the favor column, what is the row total? 105 again. What's the column total for the favor column? Yep. And the total n is still, yep. And that, I got 58.64. And I personally prefer to do them using this formula and then double check. Do they add up to 105 or, well, I think it's 105 like they're supposed to? Do they?
Yeah.
I think they do, right?
They look like it.
Look like it. And you could check with your calculators, right? You could also do 105 minus this number to get that one as well. Does that make sense? That wouldn't be incorrect. Your book does it that way, but I find it easier just to use the same formula for everything, personally. Okay, this next one's gonna be, what's the row total for the male row? 83. Column total is again over 188. I got that was about 36.64. And this one is 83 times 105 over 188. And I got 46.36 there. Should still add to 83, should still add to 83, and should still add to 105. If you don't get that, you made some kind of mistake. Do you know what I mean? Like, as in with, that's it. So the adding thing is a great way to check and see, did I do this correctly or did I punch a button wrong, which usually is the mistake that you make. Operator error. Is everyone okay with how I got the table?
Yeah.
Okay, other than the fact that the formula is a bit magic. Okay, that bothers me too. Okay, I don't actually know why that's the formula yet either. So, like, okay. Show the calculations verifying that the chi-square statistic is the 7.6 stuff. So chi-squared is that something. So you do chi-squared was equal to sum observed minus expected squared over expected, right? So for the first cell, the female opposed, what was the observed value?
37.
Minus the expected, which was
46.76.
Squared divided by 46.36. Does that make sense? That's the first one. Let's just go across the first row. So next, how many females were in favor of the ban?
68.
The expected value for that was divided by 50. Great. Next, on to row 2, we'll have
46. 36.64.
Squared over 36.64. And lastly, plus
37.
Minus
46.36.
a lot of your calculators are smart enough that you can punch this in like one go. Does that make sense? You can do like one big long string of stuff. Do you know what I mean by that? As long as you put parentheses where I put parentheses, you'll be totally fine. You should get this is about 7.66465, which is not the same thing that they had. Does that make you sad, or are you okay with that? What could have possibly made this chi-square different than that chi-square? Because this one's probably found using software. Okay?
Probably, yeah.
So if they use software, it probably did different things with the rounding, which probably used more digits. Does that make sense? So the fact that this is a little bit of discrepancy is because of some kind of rounding differences. Like if you added in more digits, like say you had 4, you probably get the exact same thing that they had. Okay? All right, so should we try one where we actually define the chi-squared ourselves? Where we weren't told what it was? You had a question about this in a different homework assignment, didn't you? Is smoking associated with divorcing or vice versa, right? So is there a relationship? Do smokers get divorced more often than non-smokers? And it turns out that there actually is a huge chi-square value here. It's crazy. Okay, so first write the null and alternative hypotheses. So H naught is that there is no relationship between smoking and divorce rate. And HA is that there is a relationship between smoking and divorce rate. By the way, some of your homework problems will break this down into like A, B, C, D, whatever. If it doesn't, if you could like label A, B, C, D like I did in the notes, it will make it much easier for the grader to grade. Does that make sense? Like first step is to write down the hypotheses. Second step is to do the table thing. Does that make sense? So kind of like keep your work organized the same way we do in the notes, because it'll make your grader's life easier, which makes her more accurate, which makes everybody happier. Take her and her 64 papers. Okay. So calculate the value of the chi-square statistic. So this involves a lot of things, right? First, you've got to find those expected values, right? So here we go. First thing, get them expected values. The thing about math class is you can English badly and it's okay. Get them. Okay, so we have yes, smoke, no, smoke, yes, divorce, no, divorce. Oh, no space, no space. That was stupid of me. Okay. So what numbers do I multiply for the first box? Row total is? Column total is, there you go, over 1669. That's approximately 177.84. Next is 485, 1057 over 1669. That gives us 307.16. You'll believe me, right? Because you can also, I'll do those calculations if you had to, right? With a calculator, of course. How about the next one? Row total is? Great. Column total is? Great. Over 1669. You get 434.16. Last one, 1184. Column total is 1057 over 1669 is 749.84. Is that okay? All right, the chi-squared is the sum of observe minus expected squared over expected. So 238 minus 177.84 squared, all over 177.84, right? What comes next?
247 minus 370.16.
Yep. Squared over 307.16. Great. Next we have 374 minus 434.16 squared over 434.16. And lastly, what do we have? 810 minus 749.84 squared you should actually verify that you can actually punch the buttons correctly, like on your own. Make sure that when you do this, you get chi-squared is 45.297 approximately. And you should say, dang, right? Dang is the right response. Holy moly, that's huge. And I can also give you a bit of a hint as to why this is happening. The expected values are what you'd think you'd see if there was no relationship. And if the difference between the relationship you saw and what you thought you should have seen is huge, that makes a big number. Does that make sense? And the dividing kind of scales it relative to the size of that group. Because there are going to be a lot more people probably in the don't smoke, don't divorce group, people who have smoked and have been divorced group. So this dividing does some kind of scaling, and this does some kind of like, how big is the difference anyway? The squaring allows for a big difference to be in either direction. Does that make sense? Like either positive or negative. That's kind of what's going on there, loosey-goosey like. So that's huge chi-squared. So, would we reject the null hypothesis with that chi-squared?
Yeah.
Oh, heck yeah, right? Tons. So here is how you find this in Excel. This is the Excel command. So you do your work finding the chi-squared from the previous part. And into an Excel, just like one little cell, you type in equals chi-dist. In for the x value, you put your chi-square statistic that you got. And this df is a variable that we will use more later on. For now, for you, it's equal to 1, okay? It changes in different situations, so you have to, that's how we would account for like having more than 2 columns, for example, okay? So for you, you would type in equals chi-dist. You'd put in 45.6, I can't speak today, I can't even read my own notes, 45.297. You put in 1 for the degrees of freedom, and that's going to tell you, when you push enter, that you have p equal to 0. It's really, really unlikely. Like it rounds, like maybe it's like 10 zeros and then a 1, but it effectively says, oh my gosh, that's really just 0. Like, just leave it already. You're close enough to 0. Which means that thing is impossible. It really just can't happen. A difference that big just wouldn't be observed. So does everyone understand how to put that in? And I think if you don't have Excel and you have something similar like OpenOffice or, yeah.
Can we scroll it down so we can see the bottom of the page?
You mean like that?
Perfect.
Yeah. So if you have like something like, there's also, like Google Sheets will do the same thing, right? It isn't just Excel, but I think the command probably is quite similar. And just Google whatever software you have that you can use, okay? All right. So based on both of those things, is the result statistically significant? Yes or no?
Yes.
Yes. And you can say because chi squared is 45 and change, 297, and that's bigger than 3.84. Or you can say p is equal to 0, which is less than 0.05, right? Either one of those is the y. If it's a test or a quiz where you have no, software, you would just have to use the chi-squared statistic thing. So in the context of the situation, write a conclusion. So what do we do about H naught? So we reject H naught. So that's not the context, that's just kind of like your first thing. So what do you say? So this means that there is or is not a relationship. There is a relationship. Between smoking and divorce rate. You could also use the word association if you wanted to. It's kind of the same thing. I did not say smoking caused you to get divorced, did I? No, nothing said that smoking causes divorce or vice versa. Just that there's an association. People that smoke tend to be divorced more. Okay, but not that it's causal. There could be other factors in there that are causing the divorce, obviously, and there probably are. But they are related. So does how to find the chi-squared make sense? Okay. Alrighty. So here are some factors that affect whether or not you get something that is statistically significant in the end. The first thing is the strength of the observed relationship, as in how different are those percentages. Like with that problem we had about the males and females and opinions about the ban on texting while driving, how different is the percentages within those two different groups? Like, that's part of what impacts how big that chi-squared. The other thing that does is the sample size. And at some point in time in the semester, we actually look at two different tables, and they have the same percentages. Like as you compute the row percentages, they're the exact same, but they have different sample sizes, and one is statistically significant, but one is not. And that's only because of the sample size. And the reason is that it's really easy to observe very sort of like rare patterns in small groups versus big groups. That's kind of the general principle. So for looking at the strength, what you do with this is this can be measured by looking at differences in row percentages. So this can be measured looking at differences in row percentages. So here's an example of how sample size matters. So for this one, I have n equals 20, and another one I have n equals 200. And I'm testing something. If you're in category A, you get 80%. Category B, you have 20%. That might be, say, like your risk of getting a headache, for example. So if category A people, they took drug A, 80% got a headache. Category B, 20% got a headache. Seems like a big difference, right? Huge. In that case, chi-squared is 1.978. P is equal to 0.16. So could you conclude that there was a difference between those two groups? No. And that's because the sample size wasn't big. Maybe you got a bunch of people who are just like headache prone. Maybe like people who have migraines, people in your group, right? Just, it's possible that that happened to you. But if you observe the same relationship with 200 people, 80% got headaches on drug 1, 20% got headaches on drug 2. In this case, chi-squared is 19.78, and the p-value is 8.7 times 10 to the negative 8th, and that's actually good scientific notation review. What would that be as a decimal without the whole times 10? How many places does decimal go backwards? 8 spots, so that's 7 zeros.
Yep.
After the decimal point, 1, 2, 3, 4, 5, 6, 7, 8, 7. Right? So you see how same proportions, different sample sizes, and that chi-squared changes drastically. Okay? So the moral of the story there is if you ever do a study, the kind of general rule of thumb is you need at least 30 people. So, and probably like more like 100-ish is better. Okay. And then the last thing I want to talk about is something called practical versus statistical significance. So for this, I want you to look at the magnitude of the relationship, and I have a really good example. So you see this headline, the risk of dying in a plane crash, and we're going to assume a commercial plane, has doubled. Okay? I'm like, oh my gosh, crazy, it's doubled. I'm not going to get in a plane ever again.
Risk of the plane crashing or of you dying in a plane?
Risk of you, we'll just say plane crashing, okay? Because it could, but we're going to assume that if your plane crashes, you probably die. Okay? Well, if it's a big commercial plane, have you heard of any commercial plane crashes? Well, I mean, there's a few, right? There's the Hudson River, okay, right? There's that one. That was kind of special.
Still crash.
It's still a crash. But lots of other plane crashes, like the plane disappears, we never see it again. We have no idea, but people. So anyhow, the point with the magnitude of the relationship, and this was actually like in your book in chapter 1, there's all these interesting little things that they kind of preview what's going to happen. And there was this example. They said, oh my gosh, the risk of, I think it was the people and the towers making an error had doubled. But the thing is, the base risk, as in the risk before, was something like 0.000000001. You double that risk, is your risk still all that high? Not really, right? So I think it was like eating cookies. Like, oh, eating cookies doubles your rate of getting cancer. But if my rate of getting cancer is this, and it just doubles my risk, it's not as if it really impacted me that much, because the risk was so low to start with. So I'm going to keep eating my cookies, or in my case, my bacon, covered in chocolate. They make that, bacon covered in chocolate. It's really good. It's not bad at all. So the point is, look at the baseline risk, as in like the risk before that change was made. So it might be statistically significant, but it's like no practical significance because you're not going to give up your bacon or cookies or airplane flying. Okay? All right. So, a statistically significant relationship was found between hormone therapy and invasive breast cancer. There were 166 cases of invasive breast cancer out of 8,506 women taking hormones, and 124 cases of invasive breast cancer out of the 8,102 taking the placebo. So what is the relative risk of invasive breast cancer when taking hormones compared to taking a placebo? So for hormones, what's your risk?
166 out of 8,506.
8506, yep. That comes out to be approximately 0.0195. For placebo, it was,
124 and 81.
which came out to be about 0.0153. So did it look so did it look all that different in terms of the risk? Not really, right? Okay, so then let's compute the relative risk. So remember, the relative risk was your risk for category A divided by risk for category B, right? Remember that from the first lesson or second lesson? So risk for hormone over the risk for not. So that's 0.0195 over 0.0153. I think I got 1.275. So if I just report that number, I say, oh my gosh, you're 1.275 times more likely to get breast cancer if you take this hormone therapy. Is that a bit misleading?
Yes.
Yeah, because the risk isn't all that different, right? So the baseline risk, so what is the baseline risk of invasive breast cancer, assuming that the placebo group is a representative of the population? So that baseline risk is, we found that in part A. 0.0153 or 1.53%, right? So you see invasive breast cancer in that much of the population anyway. And that kind of means that, the fact that they're both very small numbers just kind of made that relative risk a misleading statement. That's kind of what part C is getting. Explain why it's important to report the baseline risk found in part B when reporting the relative risk found in part A. And the kicker is that it's important to know when the baseline risk is low. To have an idea about practical significance. So that's all this is just talking about. Just be careful, and you should really, being responsible scientists or people who might use statistics, should report your baseline risk too. And the very, very, very last thing before we go away for the weekend is what to do with a non-significant result. So what this means is, suppose your chi-squared is less than 3.84, or your p-value is bigger than 0.05. So the first thing is, you don't ever, 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 ever say H naught is true. What you say instead is you fail to reject H naught. You didn't prove it's true, you just showed that it is at least plausible. So what it means in this context is that the sample results you found are not strong enough to conclude there is a relationship. And it also means that the observed relationship is not unlikely if the variables are unrelated. But there could be lots of things that are causing this. Like you could have a big difference, and the reason you fail to reject H naught is your sample size. Does that make sense? Like that could be the reason why. And you should try to get a bigger sample size and see if you can actually redo your statistics. Okay.